So in this video we will look at some of the properties of the Fourier transform which will be useful to us. Okay, sorry, properties of the Fourier series which will be useful to us. So there are several of these properties which are used especially to solve problems, and it helps us by making use of the properties. It helps us to avoid repeatedly computing the same analysis and synthesis formulations. So we can directly use the property and can get properties of desired signals if we already know the Fourier series representation of other signals. Okay, the first property is that of linearity. So in all these, in this video, most of the time we will be talking about the Fourier series of the signal x of t, which has a period t, and y of t, which also has a period t. Okay, and the general notation which you use is x of t. If you take apply the Fourier series, you get the coefficients ak, which are the coefficients of the Fourier series, of the ak are the Fourier series coefficients of xt, and bk are the Fourier series coefficients of yt. Okay, and this dual arrow means that this transforms to this or this transforms to this. So this is the time domain, this is the frequency domain. So the first property is that of linearity, which basically means that a xt plus b yt, where a and b could be complex constants. If x of t and y of t have the Fourier series coefficients ak and bk, then a linear combination of them will give you a linear combination of the Fourier series of the respective Fourier series coefficients. The second property is that of time shifting. So if y of t is x of t minus t naught, which is a time shifted, here is a delayed version of x of t is y of t, and if x of t has the Fourier series coefficients ak's, then x of t minus t naught will have the Fourier series coefficients ef minus j k omega naught t naught. So ef minus j k omega naught t naught ak. Okay, so basically what this means is that if x of t as a Fourier series representation ak, a time shifted version of xt will have the same magnitude ak, but will have an additional phase term. This is a phase term. Okay, so this is an additional phase term. So basically what this means is that if you have a signal like this, for example, and if you have a signal like this, which is nothing but the time shifted version of this signal, the magnitude of the Fourier series remains the same. Essentially the magnitude of your ak coefficients remain the same, only the phase of the Fourier series coefficients will change, because in general ak could be complex, so it could have a magnitude, it will have a magnitude and can have and it will have a phase. So time shifting does not lead to change in amplitude, change in magnitude, it only results in change in phase. So that is the time shifting property. So all these properties, this might seem like a strange result, but all these properties can be very easily derived by just substituting it into the original Fourier series analysis and synthesis formulation. Okay, so just compute the Fourier series for this and you will be able to get this formula. Time reversal is the next property. If x of t has the Fourier series ak, x of minus t, which is the flipped in time, has a Fourier series representation a of minus k. So one interesting question, what will happen if x of t is even, right? If x of t is equal to x of minus t, then what can you say about a of minus k? Time scaling is the next property. X of t is again periodic with period t. So then what will be the Fourier series coefficients of x of alpha t? Alpha is greater than 0. So if x of t is periodic with time capital T, with period capital T, x of alpha t will be periodic with t by alpha. Okay, so if alpha is greater than 1, then it means it will shrink in time, and if alpha is greater than alpha is between 0 and 1, it will expand in time. So similarly, that is how the period will also get changed. So if ak are the Fourier series coefficients for xc, x of alpha t will have the Fourier series coefficients ak, the same ak's remain, except that now the fundamental period has now changed. Now it is alpha omega naught. The fundamental frequency is now alpha omega naught because the period has changed. Okay. The next property is multiplication. This is probably a very important property, a very practically very useful property. So there is a periodic signal x of t with Fourier series coefficients ak, y of t with Fourier series coefficients bk. Both of them are periodic with period t. Then xt, yt, the product of these two functions, are also going to be periodic with time t. Then what will be the Fourier series coefficients of xt, yt? Okay, so this again you substitute it into the Fourier series analysis coefficient formula, and you will see that the term, if that is h of k, it will be like, it will have terms like this: al, b, k minus l, l goes from minus infinity to infinity. So this is, if you look at this expression is nothing but a discrete convolution. Okay, so essentially if you multiply the signals in time, this is time domain, when you multiply signals in time, the Fourier series coefficients get convolved. Okay, so this is actually a very useful property. Okay, so essentially what this means is multiplication in time is convolution in frequency, and in fact many of the properties will have a dual. So this one is multiplication in time is convolution in frequency. The reverse is also true. If you convolve in frequency, if you convolve in time, then it is equivalent to multiplying in frequency. So if you have an x of t, so what basically this coming back to this property, what this property means is that if you have two signals xt, yt, and if you want to find their product, you can compute the product by also using their Fourier series coefficients. The product will, the Fourier series of the product will be represented by convolving the two respective Fourier series in frequency. Okay. So this is an important property, multiplication. Then we will come to conjugation and conjugate symmetry. So x of t transforms to ak, x star of t, the conjugate of x of t transforms to a star of minus k. So this again has some after effects. So this means that if x of t is real, okay, then x of t and x star of t are equal. Then this also means that k and a minus k are equal. Okay. So this basically means that if the x of t is real, the Fourier series coefficients are conjugate symmetric. They have conjugate symmetry, and because of this there are other side effects on the magnitude, on the phase, on the real part and the imaginary part of the Fourier series. For example, for a real signal x of t, you will find that the magnitudes are even. The magnitude of the Fourier series coefficients ak, they are in general complex. So if you look at the magnitudes, so if x of t is real, if you are looking at the Fourier series of a real signal, the magnitudes of the Fourier series will be even. Okay, so what is there on the left side in the frequency domain, what is there on the left side is equal to what is there on the right side in terms of magnitude. In addition, to being real, if it is also real and even, then you will see that the ak is equal to ak star. Essentially this means that the Fourier series coefficients are also real. Okay, so if the signal is real and even, Fourier series coefficients are real. So we saw examples of this when we did the Fourier series of a sine wave. Sine wave is not even, but when you see when you saw the Fourier series of a square wave, okay, we found out that the Fourier series coefficients are even. The Fourier series coefficients are real. The last property is that of Parseval's relation. So in Parseval's relation, what we do is, so basically it means that the energy over time, over one period, is equal to the energy of the Fourier series coefficients. Okay, so total average power is equal to the sum of average powers over all harmonic components. This is basically nothing but conservation of energy. Energy, whether you represent a signal in time domain or in frequency domain, either with the time values x of t or with the frequency samples, which is represented by the Fourier series coefficients, the total energy remains the same, no matter which domain you are using. We will see now by using these properties. Some examples are there in the book. You can go through. There are more examples in the book. I am only touching upon 2 of them. This is example 3.6 from the book, which is the example of a square wave. Okay, you are asked to find out the Fourier series coefficients of a periodic square wave, which is called GFT. So immediately we can make use of the time shifting property, which we had seen earlier. So GFT is actually represented by x of t minus 1 minus half, because this is also scaled to half and minus half. So, so if you remember the example in 3.5, which we covered in some of the earlier videos, we had a symmetric square wave which had an amplitude of 1. So from that square wave, by applying this changes to that square wave, by these transformations, if you do, it is basically a time delay followed by a shift, by a amplitude shift. If you do this, you get GFT, which is the signal which we are interested in. But by looking at the Fourier series properties, by making use of the Fourier series properties, we can compute the Fourier series coefficients of this without having to actually compute them. So if x of t is transformed to ak, x of t minus 1 from the time shifting property will be ak multiplied by e raised to minus jk pi by 2. It is only a phase shift here. Okay, only a phase shift happens here. Then of course we have handled it for this one now. Now we should handle the Fourier series for half. That can be easily done because it is a constant. So it has only the DC component, all the other non-zero coefficients are 0, and this is a linear combination of 2 signals, this x of t minus 1 and the constant signal half. So by applying the linearity property, we get your d of k, which is the Fourier series coefficients of the signal which we want, which is this one, and by applying this, we get this formulation. For k not equal to 0, you get this one, and for k equal to 0, we get a0 minus half, where this ak are the coefficients, the Fourier series coefficients of the square wave which we saw in example 3.5. Okay. So we have computed the Fourier series coefficients dk of the given signal gk by making use of the Fourier series properties. Another example, example 3.8 from the book. This signal is known as an impulse train. It is nothing but a sequence of periodic impulses, okay, over a time t. This is x of t, and it goes over time, and it repeats, and it is represented by this, which is del of t minus kt. K goes from minus infinity to infinity. This is my x of t. How will you compute the Fourier series coefficients? This you can compute by applying the analysis formula ak, and if you substitute this and by using the property of the delta, you will see that the integral reduces to 1 by t. I mean, this is basically 1, and this you will get the answer 1 by t. And this for all k, there is no k here, right? So for all ak, you get the value 1 by t. So essentially it means that all the Fourier series coefficients of this periodic impulse train are identical. They are also real and even, because this is a I mean, like, these Fourier series coefficients are also real because the signal is real and even. So so this was that for the square wave which we saw earlier in example 3.5. So there is a relationship between this square wave and the impulse train here. This is an example of the periodic impulse train. There is a slight modification here. So if you differentiate this signal GFT, I am calling this GFT, if you differentiate this signal, you will get this, because you can consider them as step functions. So this is a step which starts, this is a step which finishes. So the derivative of the step is an impulse. So this is a rising step, so you get the rising impulse. This is a finishing falling step, so you get a falling impulse. And similarly, this is how this is. So if you differentiate this GFT, you will get this QFT. And So now if you want to find out the Fourier series coefficients of this particular signal, again you can use the Fourier transform properties. There is a time shifting property, linearity property, there is also a differentiation property. So if please, the table 3.1 in the textbook lists all the Fourier series properties which you can use. So by looking at these properties, you will be able to solve this solve and find out the Fourier series coefficients of both this signal as well as this signal. This signal anyway we have done. So for this signal you will be able to find out the Fourier series coefficients if you know the Fourier series coefficients of this one. Fine. So please see the book, table 3.1, because we will be using these properties will become very useful while solving problems.